Hello, this is Guo-Cheng from Neijiang Normal University. Today I will give a talk on recurrent layered works with short memory, a fractional calculus approach. Our talk, the content, includes 6 sections. First, let's have a look at the problem and motivation. The classical RNN becomes the one often used model in natural language processing and deep learning. It holds the following iteration structure as the equation 1, where fx is an active function. However, the memory level is not high enough and causes poor performance in big data processing. It can't capture the relationship between non-term series. So, how can we do? We record that the fractional calculus holds the memory in facts. As a result, we want to adopt the fractional calculus to improve the later network's memory in facts. But the main problem is the fractional calculus is continuous. And in the classical case, we can do the lambda difference to replace the derivative. But in the classical fractional derivative equation 5, it will be a bigger problem. For example, we should have the numerical areas by discretization of definition 5. How can we do? Generally, we have 2 methods. The first one is to do the first and numerical methods of high accuracy, but we will still have the numerical areas. Second method is to find new discrete memory in-fact tools. Fortunately, we have the famous discrete fractional calculus developed by Neijiang and Yilu. They divide the fractional sum by use of equation 6, and in the definition, the following factory function equation 7 is used, and then couple-to difference is defined by equation 8. We note that the discrete fractional calculus is a numerical one. The numerical version of the couple-to difference is defined by equation 9. The properties of the discrete fractional calculus can be found in the following reference. We can have some other useful properties as equation 10 to equation 13. In order to improve the memory level of the RNN, today we propose a weight function approach. We start from the classical RNN in figure 1, and then we input the memory function or weight function into the equation 14. Particularly, when the weight function k alpha nj equals to such a gamma function, then we can return back to a fractional difference equation like equation 13. That means we can use the theory of the fractional difference to investigate the equation 14. We can consider a special example of equation 14, like equation 15. We can see the fractional RNN holds rich dynamics. For example, in the first stage it is stable, and then bifurcation, and then chaos. These are our results for fractional RNN, which holds the same iteration structures as fractional chaotic maps. In the first paper, Professor Benialo and I successfully introduced memories into logistic map to develop a fractional one. Much more importantly, it holds rich dynamics as that of classical logistic map. In the second paper, we extend the Jacobian matrix method to distinguish the chaotic states. We start from a fractional sum equation to draw a tangent map, which is also a fractional sum equation with memory. Then we get near-proof exponents directly. In the third paper, we considered the tempered fractional calculus on time scale and obtained a different memory function, which is also a discrete one for faster image encryption. With these applications, the discrete fractional calculus for time scale plays an important role. Besides, it is also very convenient for stability analysis. For stability analysis, we considered two methods. The first one is to construct near-proof functions. The second one is to use fixed point theorem. In the method, we construct fixed point mappings and consider the existence and stability conditions together. The rest is the purification analysis. It is difficult to our team, and our group now is doing this job. However, it is a little complicated. So we can consider the application of fractional RNN. However, here we will meet some difficulty. For example, in equation 14, we can see sometimes x0, x1 are weak to xn plus 1, but always we should start from x0, and then we improve the computational cost. We should give up the no-need information x0, x1, but how can we do, and how can we treat the equation 14? And this is our short memory approach here. We proposed such a concept in 2019. Then we extended this idea to fractional logistic map, the discrete case, and then we use this idea for image encryption, variable order encryption, and the short memory approach. We can compare with the standard one. You can see we decrease the computational cost of chaotic series. We give some remarks here. In the short memory approach, we cut the interval into several sub-ones. Now, the fractional order can be different, and our approach indeed provides a new way to construct fractional order and variable order modeling. In the approach, we use the terminal value of the last subinterval as the initial value of the next one. Here, we need the global existence conditions. That means the terminal value can be used as the initial value. In the fractional modeling, we always start from the initial value for the point t0. We can get good results, but the price is high. For example, we strongly depend on numerical methods, accuracy, and speed. Since the model has no memory, the short memory fractional differential equation provides another thinking. The result of a fractional modeling may be not the best, but the price is low. We believe this thinking may let fractional calculus more powerful. Finally, we can use this idea in fractional RNN. For example, in equation 18, we can see the memory starts from j equals to k to n, but not from 0 to n. That means it is short memory. And in the application of deep learning, we can see the red is the fractional RNN result, the blue is the real data, the green is the classical RNN result. Our fractional RNN will lead to better result for alpha equals to 0.35. Now we can make a conclusion. In our talk, we propose a weight function approach for fractional modeling, And then the short memory approach is used to improve the performance. And we know fractional means memory, and this new feature we can use it in AI. And then many aspects should be considered. For example, the nonlinear dynamics, chaos, stability, and the control. These are the references we used in our talk. Thank you for your attention and welcome to visit our lab.